Hello and welcome back to Compiler Programming. Today I want to continue working on the debugger support and I'm going to try to tackle stack traces. Now, if we try to run the tests right now, we will actually see that we sort of already have a stack trace, but it is a bit of a cheating at how it is implemented. So you can see here we have like this stack location and then this stack location. Okay, so how does it work? The way that it works is we are leveraging the stack unwinding setup of Windows itself. So there is this exception handler that I have set up, and there is this flag inside of our own payload that we can store with this handler that tells if we are currently unwinding the stack or not. And if we are not unwinding the stack, then we are doing this initial stuff, which is exception and also printing of registers that was added in the last video. But and on every iteration, we execute this code, which is printing this location. This is pretty nice, but that means that we cannot sort of go up and down in the stack trace. We cannot just print it at any point in the program. This is very limited to the program termination. So if the exception happened and the Windows starts to unwind that stack, then we get this printed. But what I want to do is, like you have in GDB, you can sort of type backtrace at any point, or maybe there will be a separate instruction. And whenever that happens, we just print the backtrace. Okay, so how do we do that? Well, it will require some setup. The first thing is to be able to walk that stack. And for that, we need to again look at how the functions are actually structured. So function end, is this the right code? I haven't touched this in quite a while, so bear with me for a moment. Yeah, so this actually is not leaky anymore. Anyway, whenever we encode a function, the function has a prelude and the opposite of that, whatever is the right word for it, that does some setup with the stack and the registers. So here, what you can see is that here we save the registers, and then we figure out, depending on the size of the stack, we subtract that from the stack pointer, so the stack grows downwards. Then we have our main code for the function, which is this loop. And then at the end, this is the return handling, and we pop back the registers, and then we return, and this is just a sort of, we don't need this instruction, it's just a delimiter, so it is easier for me slightly to inspect the assembly if I have to. Anyhow, the point is that we sort of never expect the exception to happen in these parts. We only expect it to happen in our main code of the function. So whenever the exception happens, we know the address of the instruction that caused the exception, or if we just want to manually trigger the backtrace, we will still know where this would be happening, so we'll know the address. And and using that address, we should be able to get to the information about what is happening on the stack. And the reason we need to know what is happening on the stack, because when you do a call instruction, maybe I need to do some kind of diagramming. So when you do something like call Arrayx, whenever that happens, that's actually two instructions internally. One of them is sort of push rep plus size of call Arrayx, and then you have jump Arrayx. So this is what happens. Basically, we are setting the instruction pointer to where it needs to be after the call, and then we are jumping to whenever we are doing. So when we encounter a red instruction, what red does, it basically sort of pop, I don't know, it's jump pop like this. So it pops the address of the stack and jumps to it, but without using an extra register, if that makes sense. So it sort of maybe a better would be this version. So it's pop rep. So it pops from the stack and puts it into the instruction pointer register. So this is how calling and returning from a function works on the assembly level. And this is how sort of stack walking works. So we know that we will have an address of where to go back to on a stack, on somewhere on a stack. The only tricky part here is to figure out that in which function we are and what is the size of allocated variables on the stack. So going back to here, we need to know what is this variable, stack size apparent, so that we can do we can undo this sub in a stack, and we can actually read the necessary value. So this will be the most tricky part, but we can start chipping away at it, and let's see how it goes. First thing that is required is for us to not rely on the exception setup to get to this runtime function entry. Well, let's figure out how would that work. I actually already have a function that does what we need to do, or at least it partially does that. Let's actually move it a bit up. We might have to rearrange some other code as well. And looks like we do. I need to pull these ones as well a bit up. So that's that build. Right. So that seems to be just fine. What this function does is it does exactly the same search that we want it to do. We give it the full address of the instruction, and we get back the runtime function if we can find it, or if we can't, like, we just panic, which actually generates exceptions as well. So I'm not sure this is a good idea to even do this, but regardless, the first thing is to figure out if we can somehow avoid this runtime function lookup from dispatcher context and replace it with our function to make sure that just everything works. This is not really any new functionality, but rather something that we can look at. And I believe we can take the address that we are in at this context record rep variable. So this should be exactly the right address. And what I will do is I will not even replace this one with a new one. I will have them both and then assert that they are the same. So looked or dynamic function is dynamic is by name lookup result. That's fine. And what is the name of this? Okay, so we get this. And we also get the context. And for context, we need a JIT. Do we get JIT here as well as the context? Exception data JIT. Right, so we do. So that would be then, well, we can move it slightly down. Okay, so context record reap and exception data JIT. So that should be fine. And if lookup result is not function, printf, it doesn't matter. I just want to see that happening. And I'm not using assertion here because, again, when you have assertion inside of already exception handler, you're in for a very bad time. And that's really not something you want to do. So let's see what's happening. So unfortunately, right. So in the first pass, we actually get the right thing, but in the second one, for some reason, we are not. And that does make sense. The reason we don't get the right result in the second one, because reap did not actually change. And this reap changing is something that we want to do in our stack walking. Okay, so let's create a function. We'll call it win32 print stack. That function will accept, I guess, well, same thing as this really. So it will be dword 64, and let's just do it that way. I think this is fine. We can make that work. Okay, we will do this. Instruction address. It's now in one line. Okay, what do we need to do now? Well, we need to do this stuff, I guess. Okay, let's look again at this code. So we go through the builder, right? So this is an interesting thing. When we get this bit of code, we actually get the runtime function object that is useful for exception handling, but it's not very useful for what we are trying to do. Right. So we need a way to map from the runtime function object that Windows wants to our internal function builder object, because that's what we need here. And the way we can actually do that, I think, is to, in here, we would return an index instead of returning the actual object. And the way that the code set up right now is we have these sort of use struct of arrays, I guess, where indexes match. So we would have in one array, we would have an entry for the runtime function, and in the another array at the same index, we would have information that is internal to the compiler, which is that function builder that we need here. Okay, that's enough talking, I guess. What I will do is I will say s64 win32 get function index from address, and it is in the same code. Now the only difference is like this is actually fine. Difference is we return middle, and in here we would return a -1. Okay, it accepts exactly the same thing. That seems reasonable. Now we will change this code here. I would say s64 index or runtime function index is now this instruction address and JIT. That seems good. And we would say if runtime function index is less than 0, we return 0. Otherwise, we return this code. So dynamic, right? Well, we can put it here. Info function table and a runtime function index. Okay. So let's test this code first. You're missing void stuff, and you're obviously don't have any code working here. So for now, I'm just interested whether we broke the old code or not. So let's test that. And it looks like the old code still works just fine. Otherwise, this would be very broken. So let's add it to git index. So we have a state to roll back to if we need to. Okay, now we have this runtime function, and we're going to replace it with this code now. So like this, return to do let's maybe printf right away, something like unknown function address or something. So the thing with the debugging that I'm setting up right now is that it will only work for the code that is written in MetaAssembly. It will not work for external libraries at all right now. And I'm still thinking if and how I want to support that, but this could very easily happen. So when we are walking the stack, we might end up in the code that doesn't belong to us. And I think the best way there would be to like just print maybe the address. Yeah, let's do that actually. Let's print the address here. We'll just do percent 16x, and then well, actually that should be the address of the start of the function. So I will still that to do, but I will print instruction address here. Instruction address. I think Visual Studio shows it like this, and to do adjust instruction. Actually, I can even do that. Whatever. Just instruction address to point to the start of the function. Okay. So that's fine. if we did find the index, then we will do what? We will, let me take a look at the builders here. This is where we encode the functions. Right, so I think I'll just should be able to do this. Program functions, and program is what? Yeah, it's just JIT program. Okay, that seems fine. We can do that. Builder, okay, program functions. So let's say JIT program functions and runtime function index. So that should give us the builder. And if we know the builder, we can start doing nice things. So this would be like this, like this. Okay. And current offset is 0. We need a relative instruction byte offset. Okay. Hmm. In here, we would get it by relative instruction byte offset. So we need to know the function begin address, I guess, and image base. Mm. Need to think about that for a second. So as far as the image base goes, that's not really a problem. I think we can get it from JIT as well. Let me quickly consider that. So yeah, this would be in JIT program memory, something like this, I guess. We can actually try to modify it here. No, it's fine. Let's just dive right into the right place. So JIT program memory. Okay, so we have program memory, and then we have code buffer. So let's just say that the U64 relative instruction byte offset is gonna be code buffer memory. So this is like the image base, and then we need to add to it function begin address. Okay, that should also be not a problem because we can do what we had before. Runtime function. Okay, so we just add like so. And that's actually like absolute function begin address, right? And now, well, right, okay. That's absolute function begin address, and then we can copy this code and hope that it is what we want. That's this build. Let's start with that. It doesn't. So you require, right, LLX. Okay, now you're happy. We need the info. Can do that as well. Okay, we don't have dispatcher context, so instead of that, we will have instruction address. Okay, and right, so we need to convert this to U64. Okay, well, let's build. Let's try to call it and see where we end up. So we put this and we put exception data JIT. Let's see how badly I screwed this up. Well, we didn't crash. That is great. And even more than that, we actually got the first stack trace. So this is pretty cool. That means that majority of this stuff does work. Now we are ready for the next step. So let me do git add, and we go from there. So this prints a single stack entry if we know the instruction address. Our next challenge is to figure out the next instruction address. And I'm not exactly sure how do I know when to stop. So, that's actually quite interesting. There's probably a way to figure out what was the entry point to the whole program, but I don't know how that would look like. I can try to very quickly search for that. So something like Win32 find. So we need one of two things. We either need to know where the stack starts, or we need to know what was the entry point. Fine. Let's start with the stack one. Find stack base or something. Stack section base address. Get current thread stack limits. That seems pretty good. This is current stack pointer. It's not what I want. Thread information block. This might be a very deep dive, so we'll see if I want to go to here. That is very general thing. I'm not interested in that. Retrieve the boundaries of the stack that was allocated by the system for current thread. That seems perfect. Okay, so let's try to call that and see how we are doing. Right, so we actually also need to pass here the stack address. So dword 64 stack pointer, right? And that would be context record RSP. Okay, so we have this, right? Now we can call it like so. Not sure where exactly I would call this, but let's call it here. We have ulong is probably U64. No, it's pointer to, so it's like this. It's actually U32. Low limit. Is it really U32? Pointer where there's this lower boundary. It's possible for you to execute in stack memory that's outside the region allocated. Color used where the current stack pointer is within the returnal limit. Get current thread stack limits. Okay, well, it will yell at us if we are doing something wrong, so let's just continue like that. High limit, low limit, and we would have a low limit and high limit. Do you compile? So is it U64 after all? Okay, so this is perfect. We now have low limit and high limit. That means that if we get to a point where we are above stack, that is where we need to stop, I think, if we don't stop earlier, but I don't think so. So let's try to do that. First of all, let's do if stack pointer is less than a low limit or stack pointer more equals to high limit. I'm not exactly sure if high limit is inclusive or exclusive. There is absolutely no information about that. I guess it is non-inclusive, so I'll do conservative like that. We will say printf outside of allocated stack, and we will at this point exit, I guess. Okay, let's see what that does for us. Well, we don't see outside of allocated stack, so that means that this was quite successful. We are doing what we should be doing. So now it's time to get back to that original thing I was talking about when starting the video. And that was that we need to be able to know what is the size of the stack allocation for each functions. And I think we actually have that information already. We have that information because here, remember, I showed you this stack size operand, and that is out layout. Yes. So we have builder stack reserve. So if I'm right, we should be able to subtract, actually add this to the stack address, read that memory, and that memory will then give us the return address that we need to. And then we sort of just recurse until we are out of bounds of the stack. That's at least my understanding of what's supposed to happen. I have not written a debugger before, so bear with me if something does not go right. Okay. I guess what we will do is we will move this code to here. And right, we will leave this and we will do stack pointer minus equals builder stack reserve. Okay. We do that check then. And it's not very efficient, I think, to call this function on every iteration, but I'm definitely not going to worry about performance at this moment. So let's leave that for later. Stack pointer, we have that. Now we need to read the next address. So let's call it 64. Return address is like so. So we will treat the stack pointer as so we'll treat this value as a pointer to U64, and like address on the stack is 64-bit in 64-bit operating system. So this would be a return address, and we can start it all over again. So I think it may not be great that we will be doing it recursive, so well, I think it's fine. Let's just do it recursive, and we will see what is happening. I'm also not sure in which exact thread I end up, to be honest, when exception happens. If I end up in exactly the same thread, then I might see like my own calls here, maybe. We will see. Okay, in 32 print stack, we'll say return address stack pointer. Actually, it's the way around. And what? And we need to pass in the JIT. Okay, basically that is the moment of truth. We either crash and burn quite horribly, or it works on the relatively first try. And we do crash and burn quite horribly. Instruction address is more than code buffer memory. Okay. Interesting. So what I'm going to do is I will do printf 16lx /n, and then percent 16lx /n. So I want to know what is the instruction address and what is the return address. That indeed does not look very well. That value does not look like the address that we want. So first of all, let me align them on 16, so it is easier to see. Right. Yeah, those two addresses way too far apart. Like this one should be way closer. Oh, I think the problem might be. What I'm wondering is if we get the same stack or we get a new stack when the exception happens. This is what I don't know. Because if we have the same stack, then we are screwed a bit. And if we get a new one, then it should be fine. But how do I check that? Well, time to get out the debugger, I guess. So this is Win32 runtime. Let's I need to think what is the best way to debug that. All of this stuff is debugging the debugger, and exception handling is always a bit of a pain to deal with. So unwind. I guess what we'll do is we'll focus on this test, and then we'll go to here. Okay, so this should give me the address in question. We'll go to here and we start looking. Actually, we can probably bring in the registers to here because that's what we care about. This is our stack. Let's put it into here as a temporary value. Okay, so this is where the stack points to, and right. And now what I want to do is I want to, so this is the return address that I expect. So this is return. Okay, stack before. Now we will step inside of the call. And if you look at registers, so stack has shifted and it has shifted by 8. So like this is that would be, yeah, 8. So that is what I would expect. So now if I look at RSP as a 64, no. Okay, it really signed in 64. Are you okay with that? Okay. You are okay with that, and I want to think I can do something like this. Yeah. So this is what is on the stack. That is not exactly what I would expect to be there. Ah, right. What I'm interested is for this to be a pointer. Okay, okay. So this looks pretty good. It's very near to what I would expect. Right. That actually does look good. So this is the values that I expect to happen. Now the next breakpoint I want to have is a breakpoint in here. Okay, so few things. The first one is about the stack, and unfortunately it looks like the stack is actually, we are using the same stack inside of the exception handler, which kind of makes sense because exception handler should get access to the stack, but that makes the whole thing that I want to do pretty annoying to deal with. Because essentially I need to know what was the stack. Well, actually, no, I do know. I do know what was the stack location at the point where the exception happened. Okay, so let's just look at this. So all of this is fine. That's okay. Let's look at the locals and let's see what is our stack pointer. So add watch, let's put it here. Stack pointer X. Okay, and then it's A60. Well, it is roughly where I would expect it to be. Yeah, that seems fine. That seems perfectly fine. Okay, all of this stuff, that's fine. Let's just run to here. Okay. So stack pointer is now A48. Okay. I know what the problem is. At least I know one problem that I have. And that problem is I, as always, do stack in the wrong direction. Because when we do sub and like stack grows downwards, it means you need to plus here. So if you caught this before, I'm sure that at least one of you did. But it happens to me every time I work with a stack. And I know why it's backwards, but it still doesn't help me much. Anyhow, so let's get back to here. Now all the numbers are different, but we should be able to at least see if the function. I'll actually just run this since all the numbers changed anyway. Okay, so that looks pretty good. These addresses are where they should be, so I like that. Well, let's try to go for that and see what falls out next. Okay. Right. So that assertion that we have here, instead of it being an assertion, I just gonna return -1. Like if we get to here and we are if it's less than, or if it is more than plus code buffer occupied. So basically, if we don't know anything about that address, we're just gonna say, I have no idea what it is, just leave me alone. Let's try again. And see what we have. Well, look at that. We have this stack trace, which is really nice. And then we just got the last address. Now, what I can do here's first I will probably do something like that. And this will be else, and I will actually try to make it run for the whole duration. Okay, so no, I will not try to implement a generic algorithm for this, because it is possible to actually do it. You would replace this function with a more generic version that Windows actually provides, and you will get the runtime function definition for that. But the problem will be that getting to this value will require more work. I will need to deal with this thing called unwind info or unwind info. I don't ever know how to pronounce it, like this Windows specific thing. And I think I will skip that for now. I got to the point where I wanted to be, and that is I can print the addresses here. So I will actually not do that. I will stop right here. And I will just print the stack basically till the point. Well, what I will do, well, let's actually leave it like this. It's fine. That's okay. I can say stopped unwinding, stopped at external code at, yeah, something like this is sounds okay to me. We haven't really tested this branch, but that's okay. Let's try to run this again to verify that everything is working. Yeah, we have at, and we stopped at external code. That is perfect. Now that it works, let's add it to index, and I can actually replace the old code that relied on Windows to do this for us. So instead of this stuff, print register state, and that's okay. And we will do it like so. Okay. Let's try that version. Apparently I screwed something up. What did I screw up? We don't need this relative byte offset, which is great. I think we don't need this either. Okay, so this is pretty good because now majority of our loop does not depend really on the information from Windows. We still rely on runtime function, but that is actually very easy to get rid of. I just need to store a bit more information inside of my own code. But yeah, this thing is more or less universal. I think we'll need to do like minimal changes for this to work on Linux and stuff. So that is pretty cool. Again, let's see one final time it working like we want. Right, so we have unhandled exception, blah blah blah, and then we have two addresses that we know about, and then we stopped an external code. If I want to do this, I will need to like use debug help DLL on Windows that allows me to load debug information for like loaded libraries essentially. This is something that I might want to do at some point, but I'm actually not really interested in external code. There is like the whole point of this debugger is for me to be able to debug programs that I write and not debug the compiler itself. So I think that is pretty good. I guess that is all I wanted to do. This went pretty okay. I'm happy with the result as well. But obviously there is lots more to do, but not today. Thank you very much for sticking with me so far, and hopefully see you next time.